Dear students, I welcome you for the today's lecture related to the control valves in the subject of process control. Control valve, it's the heart of our industry. In general, we have seen the different examples where the control valve is used to control the different equipment, like a simple mixing tank where you want to maintain the constant temperature, like heat exchangers, like reactors, where all the flow that is controlled with the help of a control valve. It's a manipulated variable. When we have talked related to the our block diagram, there also the control valve plays a very important role. The set point R, the comparator, it compares the set point R with the measured value B and gives a certain error which is going to a controller. Then this controller sends a signal in terms of a pressure. Controller sends a signal in terms of a pressure. That is why it is P that is mentioned, which is going to a control valve. So the control valve adjusts its position. Control valve adjusts its position, that is the M manipulated variable. Adjust its position means the valve opening, how much amount of the valve that is to be opened. This is decided by the input pressure P, and this is called the manipulated variable. Depending on the amount of the opening or closing of a control valve, the fluid which is entering into the equipment, that is controlled with help of this control valve. Then there is a process. This process that can be the any different equipment like a heat exchanger, reactor, a certain specific loop into the distillation column, a heater, all these are there. Then the C output you will get, and the measuring element that is there. So in terms of a transfer function, GC, GV, GP, GC is transfer function for a controller, GV is a transfer function of a control valve, GP is a transfer function for a process or an element or an equipment, H is a measuring element. It can be a temperature measuring element, pressure measurement element, concentration measuring element, concentration or composition measuring element, flow measuring element, level measuring element. So these are the different measurement systems. Now in the last class we have discussed related to this controller. Today we are going to discuss related to the control valve. So basically what when looking at this figure, the control valve that is connected to a controller. The controller, the pneumatic controller, this is shown into this figure, and for this heat exchanger, the control valve is adjusting the cooling water flow rate. This control valve that is adjusting the cooling water flow rate which is going into the heat exchanger, so that the process fluid, hot process fluid, that will be getting cooled. Then what is a control valve? Basically, the control valve is a critical link in the process control chain in any plant. So starting of this process control, heart of this process control is our control valve. Without control valve, there is no process control. So they can be used for regulating the flow or regulating and relieving the pressures. So control valve, with the help of a flow, it controls the flow rate, it controls the level, it controls the composition, it regulates the pressure, it releases the pressure. So all these activities are done by a single control valve. So a control valve is an inline device. When we talk related to the process control, that is why it is called a inline device in the flow stream that receives the command from a controller, and manipulates the flow of a gas or fluid in one of the three ways. That is what we have talked in this flow diagram. It receives Control valve receives the signal from a controller in terms of a pressure and manipulates the fluid which is going through the process. That is what a control valve is, an inline device in a flow stream that receives the commands from a controller and manipulates the flow of a gas or fluid in the different ways. Now, what are these different ways? That is either to interrupt the flow, whether the flow should be there or whether it should be shut off. So this is the interrupt flow, that is shut off services. Either it can be fully open or fully closed. Generally your butterfly valve, they can be used for fully open or fully closed conditions. Then the divert flow to another path in a system, that is for divert service. Then third, that is the very important, that is to regulate the rate of a flow. In industrial terminology, that is called a throttling service. That is called a throttling service. To regulate the flow is nothing but a throttling service. And mostly it is your globe valve that is used. Maximum it is the globe valve to regulate the rate of a flow. When we are trying to regulate the flow rate, then we are using a globe valve. When we are trying to interrupt the flow, that can be either the gate valve or the butterfly valve. And for diverting, you are having the diverting valves, they are independent. Now these shut off services, in the open position, the flow is allowed to exit the valve. Now this is the open position. The flow is entering from this end and it is going out. Now the plug which is closing this seat, so that the flow that will be restricted. Flow is not going in this direction. So in the closed position, the flow is blocked from exiting the valve. The next is the divert valve. I am going to divert the flow now. Now this is a common entrance that is there. This is a common entrance for both the valves. But in this first case, the valve seat, the plug of this valve, this is called the plug of the valve. This is in the upward direction and your flow moves out from this outlet. That is the port A port. You call it a port or B port, whatever it is. So, and here there is a arrangement so that the flow that will be restricted. There are two outlet ports in this valve. One is this B port and the first one is this A port. But the common entry is there. Now in the second figure, the port A that is closed and the port B that is opened, so that the fluid which will enter in this direction will move in this way and will go out from the second port B. So this is the divert services. These are used for diverting the flow rate. Now in case of your petrochemical industries, where the kerosene that can be either diverted to the diesel or that can be diverted to your petrol. So such type of the valves, they can be used for diverting services. The next, that is the control. You are going to control the valve, or it is called a throttling service. Throttling service to regulate the flow rate, to control the flow rate, and this is most concerned in our chemical process industries. So control valves for throttling services, how many positions? The position of the valve determines the rate of flow allowed through the valve. So the position of the control valve or position of this plug, that decides the amount of the flow which is going out. This is your plug, and this plug, how much it is open, depending on that my fluid will move in this direction. So this is the use for throttling services. Now how the control valve actually look like in an industry. So this is a general figure in which you can see the control valve and its sectional cutout that is shown. So this is the upper part that is there. Then this upper part incorporates the actuator. Then the positioner, there is a scale that is available from 0 to 100, and this 0 to 100 indicates the opening of the valve. Now actually the valve is here. This is the body of a valve. This is the body of a control valve. Generally it's a globe valve. Now in this case, the flow will come in this direction and it will move like this. It will be moving in the upward direction and will go out from here. This will be the flow path. Then there is a plug which is available. This is a plug that is called, and this plug sits on a seat. So there is a plug, there is a seat, and on this seat there can be the plug, and which sits properly to prevent the flow. So this is my plug that is moving up and down. Depending on the position of this plug, the amount of the fluid that is entering inside this seat or the orifice of the valve. This is the orifice of the valve. Through this orifice, there is a plug which is going to restrict the amount of the flow. So the plug, when sits properly, there is no flow which is passing through it. And once you open the plug, the flow starts passing. And depending on the position of the plug, the flow rate is decided. Now this is the amount of the movement of the plug or movement of the piston that is calibrated in terms of 0 to 100. That is known as your positioner. Here the scale that is provided, this scale gives you 0 to 100% opening of the valve. And this is all regulated with the help of this pressure regulator. The input pressure from the controller that is received from the controller. Now it's an electronic controller everywhere there. So this electronic controller receives the signal in terms of the current, and this is your I to P converter. I to P, that is the current, is converted into the pressure. For this I to P converter, you are having the input from input in terms of a electrical signal that is connected here. Then there are two pressure regulators. One pressure regulator indicates the flow received to this converter, that is in between 3 to 15 psi. The pressure maximum is 15 psi, which will be receiving to I to P converter, and depending on this current I, the adjustment of the outlet pressure from this converter, that will be shown by the second pressure regulator. And this pressure 3 to 15 psi, that means if it is the 15 psi, it is completely opening the valve, and 3 psi, that is it is completely closing the valve. So in between these 3 to 15 psi, there is a 100% calibration for this valve opening. 100%, 0 to 100%, that is the opening. 15% means 15 psi pressure, that is 100% valve opening. 3 psi pressure, that is 0% valve opening. So this is the actual control valve. So actuator is one of the important aspects. Then the I to P converter, then the body of this control valve. This body of the control valve, it incorporates the plug and seat arrangement, and there are different packings which are available. Packing to prevent the leakage here, packing to prevent the leakage here also. So all these are the different packing arrangements. Now we will see the detailed figure related to the control valve. So this is the figure which we can draw it for our purpose. So the final control system component that imparts the control action and allows shift. Now this is the flow direction. The flow will come through this valve seat, and this is your plug arrangement that is provided. There is a diaphragm which is available in the actuator, and the spring which is attached to this diaphragm. The actuating signal in terms of a pressure, which is the output of a I to P converter. I to P converter, that means the pressure is the actual which is going to the control valve. So this is control valve, air, pneumatic air that is going to a control valve. It is attached to the control valve in this upper section, that is your actuator section. Then this is the valve position that is indicated. Then this is the stem which moves up and down to adjust the opening of this valve. This actuator adjusts the position of the valve stem, and this is your valve body. So the actual and how you have to draw it. One should be able to draw this control valve. Now this is the detailed figure. So this is the upper is your actuator part. Then there is a spring cylinder which is also available. Then this is your positioner. Then this is the stem. This is the actual plug that you can see. Then this is the seat ring. It is called a seat ring. Then this is the complete body of a valve. Then there is a bonnet which is connected and provided with a certain packing. the York, the side parts of the positioner and the attachment of your I to P converter. So all these are your different parts of the body. Now in this, the actuator that is separated, the valve body that is separated. Actuator and valve body, or it's a bonnet assembly also that is separated. Now the control valve properties. There are two types of control valve. One is air to open and second is air to close. That is, air to open means valve closes when instrument air is lost. Valve closes when instrument air is lost. That means it is also called the fail-safe open. Failure takes place so that my valve will be opened completely. That is the fail-safe open position. Now all this is decided by my process, which category or which type that is I am going to use, that is decided by the process. Air to open, that means now I am supplying the air so that the valve will get opened. What will happen? Air is supplied, pressure is increased so that the diaphragm moves in the upward direction. This actuator spring also pressed with the help of this pressure. The stem moves in the upward direction. As the stem moves in the upward direction, the aperture opening, the orifice opening, that will increase. So it is air to open valve. Now, if the pressure fails, so what will happen? There will be no pressure in the actuator. So this actuator spring exerts a pressure on the diaphragm and it tries to attain the normal position at that, so that this plug that will be properly seated on the valve and it will get closed. So valve closes when instrument air is lost. That is fail safe close. That is called a fail safe close. Valve closes when instrument air is lost. That is called a fail safe close. Then next category is air to close. That means when I am applying the air, the valve closes. Now look at these two figures. In these two figures, the pneumatic output signal of the controller. So this is the pneumatic output signal of a controller. This is here, you are getting it from the top. The diaphragm that is there, the spring that is also attached. Then there is a stem spring. This is also called a cylinder. The whole assembly is there in the cylinder. Then this is your body. This is the seat, wall seat. Now when I am applying, look at this wall seat and look at this wall seat. It's a conical and the cone pointing towards the bottom. Here it is also the conical, however the cone pointing in the upward direction. So as I am going to apply the pressure on this, the stem will move in the downward direction and the valve will be completely closed. So pressure to close. That means it is fail-safe open. When there is no pressure, the stem will move in the upward direction. And the valve gets completely open. This is my stem, and to this stem there is a attachment of a spring which exerts the backward movement or backward flow. So the movement of this stem, that is going to position the plug, the plug position that is adjusted with the help of this stem. Now the plug, inverted plug, this is the correct triangle which is there. The pressure is applied, the stem moves downward, and the valve gets completely closed. So this is the actual position you can see here. So this is what the plug that is there. It is in an open condition. Now the another position where it is in a closed position. So this is the closed position of the same inverted triangle. Now this is the another type of the triangle where the valve position, in this case the plug moves down, it closes. Now in this position the plug moves down, it gets open. That is the difference. This is the case where the plug moves down, it gets closed. This is a position where the plug moves down, it gets open. That is why pressure to open. Now in this case, the supply is from the top. Now in the previous figure, that is showing the inlet of the air from the bottom side. Inlet of the air from the bottom side. In the next figure, you can see the inlet of the air, regulating air, that is from the top side. So there can be two arrangements for the inlet air into the actuator assembly, one from the top and another from the bottom. So either I can use the inlet from the top or use the inlet of the air from the bottom. So there are two assemblies that can be adjusted. So depending on this, the plug seat and the valve, that will be also going to vary. So this is the actual pneumatic control valve. The important parts are your diaphragm, the cylinder, stem, then spring, the body or cylinder, then plug, valve seat. So this is the figure which you should be able to draw the valve, or you can also draw this figure also. It is also representing the same thing. So there are two types of valve, that is air to open. Valve closes when instrument air is lost. So that is called the fail safe close. Then air to close, that is the valve opens when the instrument air is lost. That is called the fail safe open. Now there can be the different assemblies of this plug. So this plug, as shown in this figure, is a conical plug. Not necessarily, it can be always a conical plug. So this is the conical plug which you can see. This is the seat that you can see. There are different types of conical shapes of this plug. This is the plug what we are seeing in the details. So this is the conical, this is also the conical, this is also the conical, and this is also the conical. So four different, or there can be many different conical shapes that can be there. The first one is a spherical. When it's a spherical, that is called a ball valve. That is called a ball valve. When the plug that is in the form of sphere, it is called a ball valve. When the plug that is in the form of conical, you are going to call it as a globe valve. When the plug is in the form of a plate, that is called a gate valve or the butterfly valve. So in the plate, it looks simply the plate that is resting on the plug, and then there is a spool valve. So these are the different forms of our plug and valve seat arrangements. So function is to pressure control, flow control, check valves, that is the non-return valves are also there. That means only one side flow that will be available. Then the directional control valve that we have already talked. If the pump is the heart of the hydraulic system, then the valve is the brain. The valves are used to perform the large variety of the governing and controlling functions. Now the actuator. One can go into the details of the actuator also. The actuators are the pneumatic, electrical or hydraulic devices that provide the force and motion to open and close these valves. These are all your actuator. There is a spring, there is a diaphragm that is available in the actuator. They can be either pneumatic, electrically or hydraulic devices. So this is what our actuator that looks like for a control valve. It incorporates the spring, it incorporates the diaphragm, that is the main parts. Some actuators can place a value at any position between the on and off position. That is, the signal of 3 to 15 psig is accepted by the diaphragm, which in turn moves the stem. So pneumatic positioner of the actuator will fail into the pneumatically de-energized position. That means fail safe open or fail safe close. When the air that fails, there is a possibility in the industry. Now we will understand with the help of one example. In a furnace, there is a supply of a fuel oil and the air to burn a flame, and also there is a steam which atomizes that fuel. Atomizes that fuel means small droplets of the fuel that will be formed with the help of this high pressure steam, so that it will burn, fuel will burn it properly. So when the failure of the air or failure of the electricity will be there in the plant, at that time, should the fuel enter into the furnace? No. Fuel should be closed. Fuel should be closed. For that purpose, fail-safe close valve should be selected for the supply of the fuel. Fuel valve should be closed. So I am going to select a fail-safe close valve for the supply of the fuel. And on the contrary, the steam which is going into the furnace for the purpose of atomization, that can continue into the furnace to reduce the temperature of a furnace. So for the steam that is serving the purpose of automation when the fuel is there, and when the fuel is cut off, then the steam that provides the cooling effect into the tubes. So the steam supply that should be open in that condition. So I am going to have the fail-safe open valve for the steam and fail-safe close valve for the fuel. So this is the purpose of the fail-safe open and fail-safe close. The interface of a control system for positional actuator is typically through an I to P transducer. Current to pressure transducer. Just as the process have time constants and dead time, valves have a time constant and dead time, which is largely determined by its actuator. So, valve manufacturers measure their value response by the parameters called T63, which is the time to take for the valve to reach to the 63% of its final position in response to a command change after the dead time has passed. We have already seen the response for the first order system. That is, in 63% or in one time constant, it attains the 63% of its value. So, this is our application of the transfer function which we have studied. Then these are also the different kinds of the actuators which is available in the industries. This is the most commonly that is used in our chemical industries. This is used for shut off or on off valve systems. The next is the positioner. Positioner, how much amount of the opening that is available, that can be judged from this positioner. A valve positioner is an accessory to a positional actuator that provides the closed loop control of the valve position. Positioner is a mechanical linkage to the valve stem and compare the command signal to the valve with the actual stem position and correct the error. Now, what is actually seen on the DCS or the distributed control system monitors and what is actually there in the field, there can be certain errors also. So, whatever the position actually shown into the field by the control valve, if it is showing the 50%, so positioner is nothing but a scale that is available, and to this scale there are markings from say 100, 50 and 0. In between there also 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90% and 100%. These are the percentage marking. My DCS that is showing say 40% on the DCS, and actually in the field it is positioning is to the 70%. That can happen. That is what a error in positioning of a control valve. But with this 60%, I am controlling the conditions in a steady state. So this positioner is a feedback controller. It too has a tuning parameter, tunes as a cascade loop. So these are the different parameters that can be associated with a positioner. Now, the CV is the symbol for valve coefficient, a measure of the flow capacity of a valve at a set of a standard condition. Standard condition में उसमें से कितना flow जा रहा है, that is going to be measured by a CV. This is similar to what we have studied in case of your orifice meter. The plug and the valve seat that acts as an orifice. The flow capacity of valve is the amount of fluid it will pass per unit time. The flow capacity is usually expressed in gallons per meter or kgs per meter, kgs per hour or meter cube per hour, whatever the unit it can have. And it is having the Q into the root of Hg and delta P. This is nothing but your flow rate equation, and Cv is your constant of the valve opening. This is actual our flow rate design equation for the orifice meter flow rate. Cv is a valve coefficient, the delta P pressure drop, and G is the specific gravity of the fluid. So this is your flow characteristics. Now there is a linear opening, quick opening, and equal percentage opening. So one by one we will see this valve characteristics. The valves are characterized by how their CV, valve coefficient, or the flow varies with respect to the position of its closed member. Now, a closure member is the internal part of a valve that manipulates the fluid flow. This characteristics is an either inherent or installed. Inherent characteristics, it is of their own. Then there are different types of valve characteristics: linear, quick opening, and equal percentage characteristics. So linear, that is the flow is linear function of a valve position. Quick opening, flow square root function of the valve position, and equal percentage, the derivative of a flow proportional to the valve position. Derivative of a flow proportional to the valve position. Valve type chosen make installed characteristics linear. Now this is the quick opening, linear and equal percentage. When you plot a graph of percent maximum flow, that means flow is from 0 to 100%, and against the percent of the rated travel, that means the travel of the plug, how much distance this plug that is traveling. Depending on that, this is mentioned from 0 to 100%, and this is mentioned from 0 to 100% the flow rate. Now looking at the 3, that is the linear percent, it is directly proportional. The percent opening is directly proportional to the flow rate. Percentage opening of the valve is directly proportional to the flow rate provided or flow rate passing through that. In the quick opening, in the initial part of the opening, that means say 50%, the valve has already attained the 80% of the flow. In this 50% opening, when we are studying the quick opening, it is the 80% of the flow that is already achieved, even though my valve opening is only 50%. But if the valve opening is 50% and the valve flow rate is achieved is also 50%, that is happening in case of a linear flow. And what happens in an equal percentage? The valve opening is 50% open, however my flow achieved is only 18%. So this is the difference for the quick opening, linear, and the equal percentage opening valve. So the inherent characteristics of a valve is the relationship between the flow rate through the valve and the travel of the closed member, as the closure member is moves from the closed position to the rated travel with a constant pressure drop. So linear, the flow linear function of the ball